Okay, so this cycle we're looking at the properties of water, like I said a little bit earlier, because the oceans are filled with water, and the way that water acts affects everything that lives there. So we need to look at the properties of water, and then we're also going to look at plate tectonics and continental margins. Okay, plate tectonics affects the profile of the sea floor, which will affect where things can live. And then the continental margins, those are the edges of the continents that actually stick into the ocean, and we'll talk about different places on the continental margin. And that kind of stuff, this kind of stuff that we covered this cycle, and like the first half of the semester really does kind of come back to haunt you for the rest of the year. So, if you don't get it now, make sure that you come in and see me for help because you're going to need to understand it. Because I'll be referring to the continental shelf and stuff for the rest of the year. So, please come and see me if you need help. All right? So, the first thing that we need to look at is like the seafloor and how it is the way that it is. Basically, back in the day, scientists used to think that the Earth was like one giant solid rock, right? And the continents were where they were, and they were staying there, and they're not moving, right? We now know that that's not true. The continents actually move in a process called continental drift. And they move at the same rate like that your fingernails grow at. Okay? So every year we move, in North America, we move slightly closer to Asia. We're moving away from Europe, slightly closer to Asia. And this process is called continental drift. Okay, so in order to be able to understand how continental drift actually works, you need to understand the layers of the Earth. So this is like throwback to 8th grade science right here. Okay? So you have different layers of the Earth. You have your core, your mantle, and your crust. Okay? The core is made up of two parts. You've got a solid inner core. Okay? It's made mostly of nickel and iron. And you've got your liquid outer core. Okay? Which is made of the same stuff, but it's just liquefied. Okay, and actually the movement of that core creates the magnetic field, which helps to protect the Earth from like solar radiation and stuff from space. So that's actually forms some protection for us. Above the core, you have what's called the mantle. Okay, that's the biggest, thickest part of the Earth, and it's made of liquid rock. Okay, so if you've ever seen like a volcano explode in real life or on TV. All of that stuff that's spewing out, that red stuff, that's magma. Okay, that's what's in the mantle. And then the crust, we like the crust, that's what we live on. Okay, that's the outermost layer, this is the thinnest, and it's the coolest, which is good because we can survive in liquid rock. We'll be back. So, here's a picture of your layers of the Earth. So the yellow is your inner core, this kind of like light orange is your outer core, and then the red part in like this purple and orange part, that's the mantle, and then the black line on the end, that's your crust. Okay? Okay, so those are the layers of the Earth. The crust, you have two different types of crust. Okay, you've got oceanic crust, which is under the ocean, and you've got continental crust, which is the continents that we live on. Okay, continental crust is much thicker. It's also less dense. Okay, oceanic crust is thinner, but it's much more dense. Okay, and you hopefully know a little bit about density. If you have a more dense thing and a less dense thing, which one will go to the top? The less dense, right? So you always get more dense things underneath the less dense things, right? Okay, that concept, that'll come into play several times today. Okay, so hang on to that. Okay, so continents moving. The guy that first came up with this theory, he kind of looks at the continents and like, you know, those could kind of fit together. You know, South America looks like it fits right into Africa. The guy that first kind of noticed this and proposed the theory of continental drift was named Alfred Wegener. Okay, Alfred Wegener. And so he proposed this theory, and the scientific community said, you're done. There's no way that can happen. Like, we have no forces that are great enough to move continents. You're ridiculous. Okay? And so they laughed at him and said he was stupid, and later he was proved correct. So, unfortunately, he was proved correct after he'd already died. I know. It always happens, yes. You always die before you get validated. So, he was dead, but we did prove his theory correct. So he proposed that all of the continents used to be together in one giant supercontinent called Pangaea. And so this is our picture of Pangaea. He also broke it down into two little smaller pieces that he called Laurasia and Gondwanaland. I don't know where he came up with those names, but that's what he did. Okay, so how do we get moving continents? Well, we now know of a force that is great enough to drive the movement of continents, and that force is a magma convection current. Okay? Hold on, I'm going to go to the next slide, explain magma convection currents, and come back to this one so you can finish copying down your notes. Okay? So here's a convection current. The center of the Earth, the core of the Earth, is super, super, super hot. Okay? Hotter than the crust. Okay? When you heat something up, does it become more dense or less dense? Yeah, right? So what does that mean? More dense or less dense? Less dense, right? And so if something is less dense, does it go above or below things that are more dense? Above. Okay, so you have magma that's down here by the core, that gets heated up, becomes less dense, and rises through the mantle up towards the crust. Okay? As it gets up to the crust, it's a lot cooler out here. That magma cools down, becomes more dense, and then sinks back towards the core underneath the less dense magma. Okay, so you get like the cyclical motion of magma rising up because it gets less dense, gets heated up, and then cooling off and sinking back down. Okay, that movement of the magma is actually the force that drives the movement of the continents. Isn't that cool? Okay, let's look at how that actually happens. So, you remember the voyage of the Challenger? Okay, and the Challenger discovered the thing called the mid-ocean ridge. Yeah? The mid-ocean ridge is that series of underwater volcanoes that runs around the entire world. Okay? At the mid-ocean ridge, that's actually where those magma convection currents break through the crust of the Earth. Okay? So it breaks through the crust of the Earth at the mid-ocean ridge. And so you have two plates that come together at the mid-ocean ridge. Right? So here are two plates. Okay? And these are underwater volcanoes. When, let's say, magma comes out here at the mid-ocean ridge, when you put super hot rock into water, what happens to that rock?
Cools down.
It cools down. It becomes solid. Right? So all of this magma comes out at the mid-ocean ridge, and as it comes out, it actually pushes the two plates apart. Okay? And then that rock hardens. And then more magma comes out and pushes the two plates apart, and that rock hardens. And then more magma comes out and pushes the plates apart, and it hardens and forms new seafloor. Okay, and so as these two plates get pushed apart by this magma convection current spewing magma out, that forces these two plates apart. You have continents attached to those plates, and the continents move. Make sense? Okay, so that's how the continents are actually moving. And the process of the plates splitting apart at the mid-ocean ridge and moving apart and creating new seafloor, it's called seafloor spreading. Okay. So if you, took the Earth, right, and you get all of this new seafloor being created, what would eventually happen to the size of the Earth? It gets bigger. It would be like a balloon blowing up, right? Is the Earth getting bigger? No. Okay, it's not taking us, super ever longer to get to Europe or to Asia, right? So the Earth is staying the same size. So that means we're creating new seafloor. That means that somewhere that seafloor has to be destroyed, right, or recycled. Okay. The Mariana Trench is one of the places where that happens. Yes, you're exactly right. So what happens is you have a continental crust, okay, and oceanic crust. Continental crust less dense, oceanic crust more dense. The two meet, okay, And the oceanic crust slips below the continental crust, okay, because it's more dense. So as it slips below that continental crust, it gets forced down into the mantle. The mantle reheats the rock and remelts it, and it gets recycled and formed back into the mantle. Cool, huh? Kind of awesome. So here's our mid-ocean ridge, right, where the volcanoes are, and so this is going to be where our seafloor is being spread apart and new seafloor is being created. Okay, and then again, here's our mid-ocean ridge running this way. And then here's a representation of the subduction zone. So the place where the crust is being recycled, where the one crust is being forced under the other, it's called the subduction zone. All right, so where one crust is slipping under the other is called the subduction zone. When these two like plates come together, they're giant hunks of rock. Okay, it's not like they're going to slide nice and easy past each other. Okay, so when the two come together and the oceanic crust starts to slip under the continental, it kind of like catches on the continental crust and kind of pulls down some of the continental crust with it, and it forms trenches. Okay, so it's like being pulled down. So some of the deepest places in the ocean are here, where there's two plates are meeting, and one's being forced down and forming this trench. So the Mariana Trench is a subduction zone, where one plate is being forced under the other.
Isn't the Mariana Trench also the oldest crust on Earth?
Potentially, I'm not actually sure.
Like, if it's
Okay, so that's how you get trenches. Isn't that cool? I think that's kind of cool. When this happens, so when you get the subduction zone happening, this crust that's being forced down into the mantle has all sorts of sediment on top of it, dirt, dead stuff. So everything that's in the water, when it dies, it falls to the bottom, okay, and then it gets carried along on that crust, and it gets forced down into the mantle. Some of the stuff that gets carried down is carbon dioxide, okay, and so when that carbon dioxide gets formed or forced into the mantle, it gets heated up, becomes less dense, and that carbon dioxide and all that liquid rock rises back through and forms volcanoes. So how many of you have heard of the Ring of Fire? Not the Johnny Cash song, but the actual like Ring of Fire, right? Okay, good. So you'll notice, here's the Ring of Fire. So here's lovely, all around the edge. And this is everywhere where there's a subduction zone. Okay, so one plate slipping under, like right here, and as it does that, okay, that stuff that gets melted rises back through and forms volcanoes.
so that's where like new islands would be found.
Yeah, that could be where new islands are being formed. Yeah, and then like Hawaii is here in the middle because that's a hot spot actually. So that hot spot's been stationary and the plates moved over it. So actually we're forming a new island on the end of the big island because the plate's moving and the hot spot's staying the same way, same place. So we're forming another island.
So it's going to be like a Cayman Island.